We're now going to look at circular motion and conservation of energy. These circular motion problems can be a little bit tricky, but we have a very specific procedure to follow to guide our analysis through these types of problems, and if you will follow that procedure, I think you will find these much more doable for you. The first thing to remember about any problem that involves circular motion and conservation of energy is to keep in mind that it is first and foremost a circular motion problem. So that is my big, bold statement here. So just because we're now studying energy, do not lose sight of the fact that circular motion problems, first and foremost, circular motion. So we have our roller coaster here, mass m, released from rest, v initial equals 0, at an initial y position h, and we are asked to calculate an expression for the force normal at positions A, B, and C. Well, let's take them one at a time. Let's do at position A. Well, the force diagram at position A has that we would have mg down and the force normal up, and that's it. It's a circular motion problem, first and foremost. Sum of the forces in the radial direction equals mv squared on r. Now, you definitely want to always put this equation down. If you don't end up using it, that's okay. But you will notice there's an m and a v squared in this equation. And look at this. Kinetic energy also always has an m and a v squared. So they will often be used together. So sum of the forces radially inward I choose as my positive direction. So force normal is radially inward. That's why it's positive. Minus mg equals mv squared on r. Force normal equals mg plus mv squared on r. And all we are doing here is taking our kinetic plus potential equals kinetic plus potential, going from the top of the hill to position A, so the top of the hill, kinetic energy is 0, started from rest. The initial potential energy, mgy, is mgh, equals kinetic energy final, 1/2 mv squared. But like we said, look at that, mv squared is in both of these equations, so all I have done to get my final answer is to substitute 2 mgh in for mv squared, and voila, we have the force normal in terms of the variables for this problem. So look at that, not very hard at all. Well, there's only two other possibilities for the types of problems they could give you on these loop-the-loops, and that's at position B. So if we look at position B, force normal is radially inward. mg, of course, is straight down. Sum of the forces in the radial direction equals mv squared on r. Same deal. We do kinetic plus potential equals kinetic plus potential because there's no frictional losses in this problem. If they don't give us friction, we don't put it into the problem. It started from rest at position A. That's why that is 0. The kinetic energy final, 1/2 mv squared. The potential energy final is now not 0 because we're at a height r, right? So we're at a height here of r, which is the radius of the circle. So that's why we have mgr for our potential energy final. Same deal. We are going to solve it for mv squared. We are going to substitute that in over here, and we will get our answer. And then we have our last possibility at the top. Force normal is radially inward. Now mg is also radially inward. So sum of the forces in the radial direction equals mv squared on r. Check. Kinetic plus potential equals kinetic plus potential. Potential final is now based on a height of 2r. Solve it for mv squared and take this and substitute it back in over here. So same deal, same procedure each time. I had room on the notes to make your notes complete for any of the possibilities that you would be given for this type of a question. For the AP test, the force diagrams, as always, are critical. You won't get this problem correct without correct force diagrams. And absolutely, make circular motion the first and foremost thought anytime you see circular motion, even if it is an energy problem.